Hello everyone, my name is Sahitya and I am a student of Ramakrishna Mission Vivekananda Centenary College, Rahora. Today I am going to give my presentation on Thomae function, its continuity and properties. So today I have divided my presentation in 5 parts, consist of prerequisites, a definition, graph, continuity and properties and observation. So Thomae function is named after famous mathematician Johannes Thomae, and it's also known as modified Dirichlet function, popcorn function, or raindrop function. Now we will recall some previous knowledges. First of all, the density property of R. It states that between any two real numbers, there exists a rational number, and also between any two real numbers there exists a irrational number. Then the epsilon delta definition of continuity. Can anyone wants to say the definition from the audience? Okay, so a function from A to R said to be continuous at x equal to x naught if for all epsilon greater than 0 there exists delta greater than 0 such that mod of x minus x naught is less than delta. It implies mod of fx minus fx naught is less than epsilon. Same as a function is called not continuous if the function from A to R a function from A to R is said not to be continuous at x equal to x naught if there exists a epsilon greater than 0 for all delta greater than 0 such that mod of x minus x naught is less than delta. That implies mod of fx minus fx naught is greater than equal to epsilon. Now the definition of Thomae function. So Thomae function is a function from an open interval 0 to 1 to real number. This is defined as fx equal to 1 by q if x is in the form of p by q, where p and q belongs to natural number and GCD of p and q is equal to 1. Basically, x is a rational number and fx equal to 0 if x is a irrational number. Now we'll saw some functional value of Thomae function. So as we say before that for the rational number f of p by q equal to 1 by q, from that we can say that f of half equal to half, f of 3/4 equal to 1 by 4, f of 7 by 11 equal to 1 by 11. And we also said that for irrational numbers the functional value is 0. So f of 1 by root 2 equal to 0, f of 1 by pi equal to 0, etc. Next, let's watch the graph of the function. So firstly I said here the maximum denominator is 3. So you can see that there are only 3 points for which we can see the functional values. These are half, 1 by 3 and 2 by 3 because my maximum denominator is 3. Now I am just increasing my denominator, the maximum value of denominator, and just look the changes. As much as the denominator is increasing, there are more and more points. So I have set my maximum limit here up to 80, and that actually the Thomae function graphs look like. Okay. So next, now let's discuss about its continuity. So this function is discontinuous at rational points and continuous at all its irrational points. Now we will going to prove the Thomae function is discontinuous at all its rational numbers. So for that, let x naught is a rational number in open interval 0, 1. So by definition, f of x naught equal to 1 by q. Now we have to find a epsilon such that for all delta greater than 0, mod of x minus x naught is less than delta, but mod of fx minus fx naught is greater than epsilon. So let delta greater than 0, then the density property of R, from the density property of R, I can say that there exists a irrational number x in 0, 1, which is lies between x0 and x0 plus delta. So there exists at least a number x, which is a real number, such that mod of x minus x0 is less than delta. And since x is an irrational number, so f of x equal to 0, such that mod of fx minus fx0 equal to 1 by q. Now, if I take the epsilon as 1 by 2q, then mod of fx minus fx0 is greater than epsilon. So there exists an epsilon greater than 0, such that for all delta greater than 0, it is possible to find a x such that mod of x minus x0 is less than delta, but mod of fx minus fx0 is greater than epsilon. Since x0 is an arbitrary arbitrary rational number, so I can say that the function is discontinuous at all its rational points. Now I just there is some formal textbook proof, so I just stop few seconds, just look at this. Yeah, so let's continue. So we have already proved for rational numbers. Now it's time for irrational numbers. So as same, let C be an irrational number and epsilon greater than 0 be an arbitrary. Now there are two cases. If the x belongs to C minus delta, C plus delta open interval, and also 0, 1 open interval, and the x is irrational number, then f of x is 0 and f of c is also 0. So mod of fx minus fc equal to mod of 0 minus 0, which is 0, it is less than epsilon. So we are done for this case. If x is irrational. Yeah. What is? This delta is delta greater than 0. I have choose that I choose delta greater epsilon greater than 0 and also delta greater than 0, and I take the distance delta distance from x from C both side.
Basically, you want to consider this delta neighborhood of C
Yes, delta neighborhood
in,
of C
inside 0, 1.
inside 0, 1 open interval 0, 1.
Yeah, yeah. Please continue.
So we are done for if x is irrational number. Now case 2, if x is in delta neighborhood of C and intersection open interval 0, 1, and the x is rational number. So since x is a rational number, x is in a form of m by n, and by definition f of x equal to 1 by n. And now we have to show that mod of fx mod of fx minus fc, which is equal to 1 by n, is less than epsilon. We have to show that. So basically we have to show that 1 is less than small n epsilon. Now by Archimedean property, I can say that there exists a capital N belongs to natural number such that 1 is less than capital N epsilon. From there, I can say 1 by capital N is less than epsilon. Now, for all small n greater than equal to capital N, 1 by small n is less than 1 by capital N. So the mod value of fx minus fc, which is equal to 1 by small n, this is less than 1 by capital N and less than epsilon. So we also done for those rational numbers whose denominator is greater than capital N. Now just we have a one part left for those rational number whose denominator is less than equal to capital N. Capital N. So before going to next main proof, we just watch a lemma because this lemma is required for the rest proof. So this lemma states that if my denominator of of a rational number is bounded by n naught belongs to rational number, then there are only finite number of rational numbers. So I take a rational number, let I take a rational number x, which is in m by n form, and it is in open interval 0, 1. So I can write that 0 is less than m by n less than 1. This implies 0 is less than m less than n less than n less than equal to n naught. Now, if I took n naught equal to 1, then I have no choice of m, because if I choose m greater than equal to 1, then the m by n will be greater than equal to 1, but my m by n belongs to close interval 0, 1. So I have no choice for m here. So my choice of m is finite for n not equal to 1. Next, if I take n not equal to 2, then I have only choice for m is 1, means that's 1 by 2 only. So for this case also, the choice of m is finite. If I take n not equal to 3, I can choose a value of m only 1 and 2. For this case also m is finite, and for n not equal to 4, I can choose the value of m is 1 and 3 only. I cannot choose 2 because GCD of 2 and 4 is 2, which is not equal to 1. So 2 by 4 is not allowed here. So I can choose the value only 1 and 3. So for this case also, m is finite. So continuing this process, I can say that if I take n not equal to n naught, means the maximum value, then I have only choice for m is from 1 to n naught minus 1. Means I have only n naught minus 1 choices. So for this case also, choice of m is finite. So I can see that for this case, the choice of m is finite and choice of n is also finite, because n is between 0 and n naught. So this finite number of n and finite number of n can make distinct pair finitely. So there are only finite number of rational numbers in 0, 1 when the denominator is less than equal to n naught. Now back to the proof. Now back to the proof that I consider a set S, which is consist of those rational number in 0, 1 whose denominator is less than or equal to capital N. Now I just saw in lemma that the set is finite. So let's enumerate the elements of set S by x1, x2 to xk. Now I am taking the distance of this xi and c as delta I. So mod of xi minus c is delta I. And taking and choosing a delta greater than 0 such that this delta is minimum of all delta i's. So there exists a delta greater than 0 in the delta greater than 0 such that means if I take this interval c minus delta plus c plus delta, then there are only those rational number whose denominator is greater than n, because I just rush out those um, rational numbers whose denominator was less than equal to capital N by taking the minimum of their distances. So now in the open interval of c minus delta and c plus delta, there are only those rational number whose denominator is greater than capital M. And now we already see that for this case, we are already discussing case 2, that for the rational number whose denominator is greater than n, this is the mod value of fx minus fc is less than epsilon. We already proved it in case 2. So we have covered all three cases, that if x is irrational, if x is, if the denominator of x is greater than n or less than equal to n, all these three cases we have covered. So we can say that the function is continuous at c. Now c is arbitrary, so from that I can say that the Thomae function is continuous at all its irrational points. Now this is also the formal textbook proof that what I discussed previously. So I am just stop for some seconds to watch it. Okay, so I am continuing. Uh, we are now almost the end of this topic. So
Sahitya?
yes, ma'am.
Yeah. So I'll stop you here. So for a question,
Yes.
so is your function is what about the continuity at x equal to zero?
X equal to
Zero.
huh, so for x equal to 0, f of okay, so please give me a second.
Yeah.
So I made this function from open interval 0 to 1. I
Okay.
I considered this function from open interval 0 to 1. So I cannot say about 0. In my definition, I said that uh,
Function is from zero one to.
in my definition, I said that this is a function from open interval 0, 1 to r.
So if your function contains zero, so what about its continuity at zero? Will it be continuous at zero?
Uh, oh, so if it's contains 0, so basically then I cannot write it by p by q form, all this p by q form, because this function, the definition says that this is one, the functional value is 1 by q if the gcd of some gcd of numerator and denominator is 1. So if I take numerator as 0, so gcd will not equal to 1. So this is, so I cannot say that the functional value is 1 by q, and also 0 is not an irrational number, so I cannot say its functional value is 0, so I cannot conclude about 0. Yes, ma'am.
So you can check what is the continuity of this function at zero maybe later.
Yes,
Uh,
ma'am.
when you are taking x equal to zero, so the like this one by q form it will not come because p and q you are choosing from the natural number, right? So it is also not coming in the first place. And zero you can check. Okay.
Ma'am, your voice is breaking at the last,
Yeah.
please.
So I am saying when you are taking x equal to zero, so
Yes,
in the first one it won't come because p and q you are choosing natural number, right?
natural number.
So
Yes.
automatically it is not coming in the first place.
Huh.
But when you are taking x equal to zero, so you can check whether I mean how it will look like. Okay,
Okay, ma'am.
you may continue. Thank you.
Yes, thank you, ma'am. Okay, so now we'll see its properties and some observations, that Thomae function is Riemann integrable, and the limit of Thomae function is exist at every its real number, and the limiting value is 0. And the small observation that Thomae function is continuous at irrational and it's discontinuous at rational number, but there is no function which is continuous at rational number but discontinuous at irrational numbers. So thank you. I am concluding my presentation here. Thank you MTTS and Cardiff members to give me this chance. Thank you my listener. I hope I can deliver some interesting facts about Thomae function.